State and prove the rule for checking if a number is divisible by 3. To do this, we first need a lemma. And the lemma is that 3 is always a factor of 10 to the k minus 1, no matter what the value of k is. Proof, there's actually about 3 reasonable proofs of this, so let me just write down all 3 of them just to give you the idea. First is the most intuitive one, that 10 to the k minus 1 is always going to be a string of 9s. 9, 9, 9. It's always going to be a string of k9s. So either 9 or 99 or 999 or 9,999, some string of 9s. And clearly that's a multiple of 3, since each digit is a multiple of 3. So that's the most intuitive proof. Proof number 2 is that 10 to the k minus 1 is equal to 10 to the k minus 1 to the k. And we have a rule for factoring the difference of kth powers. And it goes like this. 10 to the k, 10 minus 1 times 10 to the k minus 1 plus 10 to the k minus 2 times 1 to the first plus 10 to the k minus 3 times 1 to the second, and ending with 1 to the k minus 1. And so that's equal to 9 times some integer q. And clearly that is a multiple of 3. And you'll notice that this multiple of this q here is actually a string of 1s, if you think about it. It's 1, then a 1 in the next digit, then a 1 in the next digit, and so on. And if I were to factor 9 out of this, that's exactly what would be left. It would be 9 times a string of 1s. So that's the second proof. The third proof, which is a little bit more formal, will be a proof by induction. Okay, so let's do this by induction. So k equals, well, let's just start with k equals 0 as our base case. 10 to the k minus 1, or 10 to the 0 minus 1, would be equal to 0. And 3 is going to be a factor of 0. In fact, everything is a factor of 0. So that's that. So we'll assume the base case, or the inductive case, so assume that. Three is a factor of 10 to the k minus 1. Then we go to the next case, the inductive step, k plus 1. Then 10 to the k plus 1 minus 1. Okay, so the trick here is to introduce the thing that we know, which is 10 to the k minus 1. So we know that 10 to the k minus 1 is a multiple of 3. So let's add and subtract the 10 to the k term. And I have the 10 to the k plus 1 term is left over. Okay, so by induction hypothesis, 10 to the k minus 1 is 3 times some integer by the inductive hypothesis. So that's the last two terms. The first two terms, we can certainly factor 10 to the k out, leaving 10 minus 1. So that's equal to, and so I should say here, by induction hypothesis. And so this is equal to 10 to the k times 9 plus 3q. And that makes sense. If you have 10 to the k plus 1 minus 10 to the k, that's going to be something like 90 or 900 or 9,000 or 90,000. 9 times 10 to the k. And so this is equal to 3 times some other integer q. If I factor a 3 out of both terms, there's going to be some integer q left, where q is equal to 3 times 10 to the k plus little q. And so that means that 10 to the k plus 1 minus 1 is a multiple of 3, and so that ends the proof. So there's 3 different ways of doing this. Okay, so now that we have this lemma, we can now state and prove the rule for checking if an integer is multiple of 3. So the rule goes like this, theorem. So let's write n in our usual base 10 representation. A sub I minus 1 times 10 to the I minus 1 plus, and so on, plus a sub I times 10 plus, or a sub 1 times 10, pardon me, 10 to the first, plus a sub 0 times 10 to the 0. Then 3 divides n, if and only if 3 divides the sum of the digits a sub I minus 1 plus a sub 1 plus a sub 0. So that's the statement. The proof of this so 3 divides n, if and only if. Well, n is equal to the thing on top, so let me just rewrite that. A sub I minus 1 times 10 to the I minus 1. Going through, and now let me put the hundreds digit in. A sub 2 times 10 squared plus a sub 1 times 10 plus a sub 0. Okay, now if a number is a multiple of 3, if and only if I add or subtract a multiple of 3, it's still a multiple. So that's if and only if 3 divided by. Now let me just copy this onto the next line, because that's exactly what I'm going to do. So 3 divides that, minus a very carefully constructed number, minus a sub I minus 1 times 10 to the I minus 1 minus 1 minus a sub 2 times 10 squared minus 1 minus a sub 1 times 10 minus 1. And I don't need to worry about the a sub 0 term on this thing that I'm adding. Now the reason this works is because if that's a multiple of 3, let's start with this. If this is a multiple of 3, by the lemma that we did, this thing that we have subtracted is also a multiple of 3. That's 9, that's 99. This is a string of 9s. And so I multiply those by integers, because in a base 10 representation, all the a's are integers. And so this is a multiple of 3. This is a multiple of 3, and therefore the difference must also be a multiple of 3. Also, it's an if and only if. I know that this is a multiple of 3, then if I add the same thing back, then the original thing must also be a multiple of 3. Okay, so then finally we do the cancellations. A sub I minus 1 times 10 to the I minus 1 minus 10 sub a sub I minus 1 times 10 to the I sub minus 1. Those cancel. And what's left is going to be minus a sub I minus 1 times negative 1, which is a sub I minus 1. On this term, a sub 2 times 10 to the second minus a sub 2 times 10 to the second, those cancel, leaving minus a sub 2 times minus 1, which is a sub 2. Then over here, a sub 1 times 10 minus a sub 1 times 10 cancel, leaving minus a sub 1 times minus 1 for plus a sub 1. And then there's a plus a sub 0 here, which was not canceled out. And so that is the statement of our theorem. So we use the lemma that we stated earlier, and also the lemma from class, that if a number is a multiple of 3, if and only if that the number minus a multiple of 3 is also a multiple of 3.